All right, let's dive in. Today, we're going to crack the code to the fundamental language of the universe itself, chemistry. I mean, everything around us is written in this language. And you know what? By the end of this, you'll be able to read it too. So let's start with something you probably see every single day. Take a look at this. This is the caffeine molecule. And that jumble of letters and numbers, C8H10N4O2, that's its chemical formula. It might look super complex, but it's really just a recipe. It's the same kind of recipe that describes the salt on your food, NaCl, or even the water you drink, H2O. They're all written in this secret code. So that's the big question, right? How do we take these strange-looking formulas and turn them into something we can actually understand? Well, to do that, we have to start small. Like really, really small. Yep, we're going inside the atom. This is the ultimate building block of all matter. You see, if we want to read the recipes, we first need to understand the ingredients. And the most fundamental ingredient of all is the atom. Every single element you see on the periodic table is made of these things. But to really get it, we need to go one level deeper. Atoms themselves are actually made of 3 even smaller, or subatomic particles. And these guys are the real keys to cracking the code. And you know, it all breaks down pretty simply. In the very center of the atom, the nucleus, you've got protons, which are positively charged, and you have neutrons, which have no charge at all. They're neutral. Then you've got the negatively charged electrons just whizzing around the outside in orbits. Just remember these 3 players: proton, neutron, electron. They are about to become very, very important. Okay, so wait a minute. If all atoms are made of the same 3 particles, what makes an atom of carbon so different from an atom of gold? What gives each element its unique identity? Well, the answer is hiding in plain sight on the periodic table. Each square, just like this one for lithium, is kind of like an element's ID card. It tells us everything we need to know to identify that specific element, and it all comes down to one very special number. And that special number is called the atomic number. And the definition couldn't be simpler. It's just the number of protons in an atom's nucleus. That's it. This number is like a fingerprint for an element. It is the one thing that makes lithium lithium, and not something else entirely. So this is the key takeaway, the most crucial point. If you change the number of protons, you change the entire element. That number alone determines what the element is. And here's a little pro tip for you. In a stable, neutral atom, the number of negative electrons will always equal the number of positive protons. They just balance each other out. Now, the other key number on that ID card is the atomic mass. This is pretty much just the weight of the nucleus, which you can figure out by simply adding the protons and the neutrons together. This also gives us a great little trick. To find the number of neutrons, just subtract the atomic number from the atomic mass. Easy. But just when you think you've got it all figured out, chemistry throws us a little plot twist. What if atoms of the same element could actually have different masses? Well, welcome to the weird world of isotopes. And this little twist is the key to everything from carbon dating ancient artifacts to modern medical scans. This definition really says it all. I like to think of isotopes as siblings. They all share the same last name, the same identity, because they have the same number of protons. But they have slightly different weights because they're carrying a different number of neutrons. And this is the perfect example. Let's look at carbon-12 and carbon-14. They both have 6 protons, right? That's why they are both, without a doubt, carbon. But carbon-14 has 2 extra neutrons, which makes it heavier and a little bit unstable, which is exactly what lets scientists use it for things like radiocarbon dating. So same identity, different mass. That's an isotope. So how on earth do scientists keep track of all these different versions of elements? They use a nifty shorthand called standard atomic notation. It's a super efficient way to show the exact makeup of a specific atom just by glancing at it. Let's use lithium to see how this works. On the left, the periodic table tells us lithium's atomic number is always 3. But notice the mass, 6.941. That's actually an average of all the lithium isotopes found in nature. To describe a specific isotope like the common lithium-7 over here on the right, we use the mass number, which is just the total protons and neutrons. So here, the top number is the mass number, 7, and the bottom is the atomic number, 3. All right, deep breath. We've learned the alphabet, protons, neutrons, electrons, and the basic grammar of atoms. Now we can finally go all the way back to that caffeine molecule
and decode the recipe for good.
A chemical formula really only has three main parts. First, you've got the element symbol, like H for hydrogen. Then you have the subscript, that little number that tells you how many atoms of that element are in the molecule. And sometimes you'll see a coefficient, a big number out front that multiplies the whole shebang.
Counting the atoms in any formula is a simple four-step process, and getting this down is the first step to understanding how chemical reactions actually work. Okay, step 1, identify your elements. Step 2, read the little subscripts. 3, if you see brackets, you multiply everything inside by the number on the outside. And finally, step 4, if there's a big coefficient out front, you multiply everything by that number.
Okay, let's put it into practice with a kind of tricky one, aluminum sulfate. So we see Al, S, and O. For aluminum, the subscript is 2, so that's easy. We have 2 atoms. Now for those brackets. Inside, we have 1 sulfur atom and 4 oxygen atoms. We just multiply both of those by the subscript outside the brackets, which is 3. So 1 times 3 gives us 3 sulfur atoms, and 4 times 3 gives us 12 oxygen atoms. You add them all up, and you get a grand total of 17 atoms. See, not so scary after all.
And just like that, you've cracked the code. For real. You started with these tiny little particles inside an atom, and now you can look at a complex chemical formula and know exactly what it means. You can read the basic language of our universe.
So the only question left is, with this new skill, this new ability to read the fundamental recipes of reality, what are you going to choose to explore next? The language of the universe is now yours to read. Thanks for tuning in.